is as shown here, the concrete constitutive models for implicit and explicit solvers. So recently, the structural engineering community has observed a significant requirement and difficulties in simulating structural systems with concrete material. For example, the figure to the left shows the comparison of an RC panel test under biaxial compression tension load. As shown in figure 1, the ABAQUS concrete models, which are named concrete damage plasticity model and the ABAQUS smeared cracking model, both notably underestimate the capacity and stiffness of this RC panel compared to the test results. In addition, figure 2 shows the computation time versus the number of CPUs used for both explicit solver and implicit solver. As shown in figure 2, the explicit solver can notably reduce the computation time when the CPU increase from 2 to 128. However, for implicit solver, the computation time first decrease, and after reaching 16 CPUs, the computation time increased notably. Therefore, the development of high-fidelity models in both implicit solvers and explicit solvers are required. For large structures, explicit solvers are more highly wanted for the simulation time. In addition, the code simulation using various solvers has become a heated research topic recently. The code simulation technique is a function for runtime coupling of ABAQUS and other analysis programs. For example, a user can use ABAQUS to couple an ABAQUS standard model, which uses implicit solver, with the ABAQUS explicit model, and the code simulation interface can connect these different elements directly. It can also be extended to other software solvers and even solid fluid interaction. For example, in civil engineering, the beam and columns can be simulated using fiber beam column elements using the ABAQUS implicit solver, while the shear walls and structural joints can be simulated by shell elements or even solid elements using the ABAQUS explicit solver. The overview of this report is as shown in this figure. First, the formulation of the constitutive models is briefly reported. Second, the constitutive models is validated by uniaxial loading tests. Finally, the developed model is validated by RC panels and RC containment tests. First, we developed the orthogonal crack model for multi-layer shell element based on the decoupling assumption. The decoupling assumption assumes that concrete stress can be decoupled in the crack coordinate system upon initial cracking. Therefore, the biaxial model of concrete can be assembled directly from these uniaxial concrete models in the crack coordinate system. After the stress updating in this crack coordinate system, the stress can be rotated back to the global coordinate system. In addition, in this research, we developed both the complicated uniaxial model of concrete, as shown in this figure, this stress strain curve on the hysteretic tensile and the compressive stress, and also the simplified uniaxial model of concrete for design purpose. For reinforcement, the uniaxial model considers the Boschinger effect, as shown in this figure. In addition, in our formulation, we adopt the fixed angle crack formulation, which is helpful for obtaining stable results in ABAQUS explicit solver. This figure shows the modules of the proposed model, including the skeleton curves, the uniaxial hysteretic models, the biaxial models, and the interface to ABAQUS software, including ABAQUS UMAT and VUMAT subroutine. A detailed discussion of these modules are illustrated in this reference. In addition, the one-dimensional model, as shown in the left, can be directly used in fiber beam column elements in ABAQUS software using UMAT and VUMAT interface. This figure shows the flowchart for the proposed model. As shown in this figure, a total of 4 submodels are developed in this research for two-dimensional simulation of concrete, including a simple rotating angle crack model as a most simple case, a two-way crack model with simple constitutive model, a two-way crack model with complicated hysteretic response, and a four-way crack model. These 4 models form a toolbox in the ABAQUS software. Based on the aforementioned two-dimensional version of RC models, a three-dimensional fixed angle crack model has been developed in ABAQUS software to be compatible with almost all solid elements. This page shows the overview and the overall flow of this three-dimensional concrete model. This model is also compatible with both the implicit solver and the explicit solver in ABAQUS software. This three-dimensional fixed angle crack model has been validated by uniaxial test of concrete, including the uniaxial test and the biaxial test, and also we simulated the performance of steel plate concrete composite shear walls in this research. The figure to the left shows the comparison of the test result of a plain concrete member under uniaxial tension load. The tensile stress versus the tensile strain curve of concrete is well predicted by the model, and also the loading and unloading behavior are also predicted well. For the composite shear walls, a large amount of composite shear walls are simulated using these three-dimensional solid elements and the developed models, and the influence of interface slip on the simulation result is investigated. Subsequently, the developed two-dimensional model is validated by uniaxial loading. In this second part, we are focusing on the comparison between the ABAQUS implicit solver and explicit solver results to make sure the results are almost the same. First, we simulated a hypothetical RC member with a single rebar at the center under uniaxial tensile load. We simulated this is the stress strain curve of this hypothetical RC member under uniaxial tensile loading unloading. And for each figure, there are 2 results. One is explicit solver and another is implicit solver. As shown in this figure, the results from these 2 solvers almost coincide. Therefore, in addition, we also investigated the mesh sensitivity. When we increase the number of mesh from 1 to 100 elements, the results almost coincided. Therefore, for uniaxial tension loading, the mesh sensitivity issue was not observed. Second, the uniaxial compression load is applied to this RC member, and the results, the stress strain curve from both the ABAQUS implicit solver and explicit solvers are consistent. It is observed that these are the axial strain plot. As shown in this figure, when the mesh size increase from one element to 100 element. In this test, the axial strain is localized in a single layer of element in both solvers. Therefore, the softening. In addition, in this simulation, the softening branch of concrete is kept constant. Therefore, the mesh size has a significant influence on the descending branch. However, if the compression softening curve of concrete is modified using the element length, the mesh sensitivity issue can be reduced. In addition, we conducted the tension compression loading on this RC member, and the tension compression curve of both explicit solver and implicit solver shows similar results. The mesh sensitivity is also observed for this test in the compression side, because here we didn't modify the compression softening curve of concrete. In this page, we further increase the compression strain of concrete to 3%, as shown in the last figure. When the compression strain of concrete reaches 3%, the different results can be observed between implicit solver and explicit solver. However, this case is very hard to be observed in engineering structures with concrete, because concrete had fully lost its capacity under such a high compression strain. Subsequently, the developed models are validated by RC panel tests and also RC containment tests in this research. The panel tester or universal panel tester have been developed in University of Houston and also in Toronto University for many years. The panel test machine can apply uniform shear stress state to a structural member. As shown in this figure, it applies the compression load in one direction and the tension stress in another direction. And using the stress transformation, we can know that this stress state can be converted to the pure shear stress state. To simulate the RC panels tests, we adopt a method proposed by Huang et al. To convert the force boundary condition in the panel test into displacement constraint and permit the mesh sensitivity test. In addition, to apply the load to the boundary, we recommend to use the coupling with slave type of surface in order to ensure smooth distribution of external force to the boundary. This table shows the test metrics compared in this research. The monotonic tests were reported by Vecchio. However, in the original literature, some specimens failed in H-failure mode or premature failure mode, and the premature failure specimens were not simulated in this study. In addition, we use the observed cracking load to calibrate the FT instead of the material test result, because the shrinkage or other effect may reduce the tensile strength of concrete notably in this panel test. This page shows the comparison of specimen PV3, PV4, PV10, and PV28 using both implicit solver and explicit solvers. In general, for all these specimens, both solvers well agreed with the test, and the mesh sensitivity issue was not observed in this simulation. In addition, The implicit solver with only one element notably overestimate the stiffness and strength of these panels. Therefore, we propose that at least 4 elements should be used for simulation of panel tests if we are using this modeling scheme. Subsequently, Mansell and Xu reported a panel test program, including the CA series and CE series. The CA series has reinforcement in 45 degrees compared to the loading direction, and the CE series has reinforcement parallel to the loading direction. The test result shows that CE series has notably higher stiffness and ductility compared with the CA series. In this study, we simulated all these CA series and CE series. This figure shows the results of CA series. As shown in this figure, the mesh size varied from 4 elements to 25 elements. And the simulation results showed that both the explicit solver and the implicit solver obtained accurate prediction of the hysteretic panel test results in terms of capacity, cracking load, pinching effect, and descending branch. The developed model is also compared to the CE series. It is observed that for specimen CE2, the model underestimated the ultimate capacity. However, the energy consumption, as shown in these figures, are well predicted by the developed model. In general, the accuracy of the proposed model for the panel test specimen is validated. In addition, this figure shows the design, testing, and the results of design and testing of an RC nuclear containment vessel as reported by Lu 5 years ago. So these are two 1/13 scale tests of RC nuclear containment, and the reinforcement ratio in the RC containment is 2% for each specimen. The specimen number 1 has no additional dowel bars at the top and bottom, so specimen 1 failed in sliding failure mode. In contrary, specimen 2 added these dowel bars or end bars at the top and bottom section, and the specimen 2 failed in shear failure mode. In this study, we simulated both specimen 1 and specimen 2, and these are the shear force versus displacement curves. As shown in this figure, the load versus displacement curves are accurately predicted by the developed model. And in this section, we are using the ABAQUS implicit solver. Furthermore, the difference between these two specimens are also well captured by the developed constitutive models. Finally, the developed model still slightly overestimates the residual capacity of specimen number 1. As you can see here, the residual capacity is overestimated because the test result shows a shear sliding failure mode. In the future, we may further calibrate a detailed model for the shear sliding failure mode and improve the simulation accuracy for this kind of failure. The following conclusions can be obtained. The first, the developed uniaxial model of concrete considers this major effect of concrete in hysteretic loading, and the mesh sensitivity issue can be reduced by adapting the softening curve of concrete, considering mesh size. Second, a set of 2-dimensional and 3-dimensional models of concrete are developed based on the decoupling assumption for shear elements and solid elements. Third, the difference between the ABAQUS implicit solver and explicit solver is small from engineering point of view. Number 4, the pinching effect and shear softening effect in the panel tests are well predicted. Finally, the tests of 2 RC containment vessels are also well simulated in this research. For the future work, number 1, we have observed a rapid growth in the application of GPUs in finite element simulation. So in the future, we want to implement these models into the GPU platform so that we can further increase the speed of simulation. Number 2 is that we can possibly develop some machine learning based constitutive models of concrete to further increase the accuracy. So this is of my presentation. Thank you so much.